In this segment, I'm going to talk about Pythagoras and the Pythagorean theorem for triangles, and I'm going to be using the Geometry Sketchpad software to show you. A lot of teachers work with Pythagoras in triangles and start off with a triangle and start talking about the sides of the triangle. But I like working with squares to start off with and the formation of that, and make sure the students understand the pieces that are involved. So here I have a square in the middle that I can change its size. So I make my square however big or however small, and I can turn it around whichever way I like. So I'm going to start off my square, and we're going to call it capital A. So that's the square, the area is called A. Any length of that side is a small a. So this side here multiplied by this side going up, we've already talked about the area model before. An A times an A produces an A that is in the shape of a square. So we're going to call that capital A. And so I'm going to have the length of side A, and as I change the size of my A, my computer here calculates the length of side A. So if I wanted to find the area of box A or square A, I would need to go A times A or A squared, and I would produce an area of 8.26. And as you can see, as my side gets smaller, so let's see if I can get it down to about a 1. That's pretty close there. Then I'm going to have 1 by 1, which is an area of 1. And if I can grow it up to about a 2 or so, 2 times 2 is going to be about a 4, so 1.98 times 1.98, or 1.98 squared, gives me an area of 3.94 centimeters squared. Now Pythagoras is playing around with squares and triangles, and he noticed that if I make another square here, I'll just do that, and if I made a square and I hook it up down here so it produces a right angle down here, I can produce 2 squares, and then I can make another one. Let's see, I think it starts up here in this direction, and I can make a third one. And there's a relationship between these squares that is called the Pythagorean theorem, and we're going to talk about that in just a sec. So here I have my 2 squares with my right angle occurring down here, and if I produce a third square and I hook it up something like this, then I can produce a third square. And Pythagoras says that if I take the area of this square here, this yellow square at 15.3, and I add it to the area of this b squared, 11.7, I should get an area that is of this square here. Let's change its color, whose area is these two areas added together. And so here it is at 27.08. And just to show the dynamic aspect of the Geometry Sketchpad, if I was to take these and make all my pictures smaller, so now instead of having quite the same size, I only have an area of 8 and an area of 6. Together that gives me an area of 15. So 8.5 and 6.5 gives me an area of about 15. And it does the actual calculations for me. And I can show that if I make my squares really large, the same thing happens. 40 plus 30 gives me 70.93. And I can make them quite small. I can rotate them around. I can still get the exact same. This box plus this box equals that box. And so this is the idea of this square plus this square, the area of this square plus the area of the orange square together add up to the area of the blue square. Often when we're working with Pythagoras, though, we're not really worried about the squares. We're actually looking for the length of this side here, or the length of one of the sides of my triangles. So if I know the area of my whole square, as we talked about in this first diagram here, if the length of the side is A, the area is a capital A. Switch over to here. If I know the area of this big blue square is 18.95, to find out the area or the length of just this side, I want to do something called the square root. And that's what this symbol here is for. That square root symbol asks me to find what is the length of the side of my square. That's what that symbol talks about. And so the square root of 18.95 is 4.35. So this length here would be 4.35. centimeters. I think this is also a good time to talk about the units that we're talking about. Since we're talking about area, area is calculated by length times width. It's a two-dimensional space that's covering a two-dimensional surface, so therefore it needs to have this 2 up here. So my areas are always in square units, but the length of a side is just a length. It's one-dimensional, so therefore it only has centimeters to the first, or just centimeters. So whenever I do a square root, I'm going to change the exponents that are found in my units, because I'm asking to talk about different pieces, different parts of my picture. So in this question, I have a small square here, and I have my large square here, and I'm looking for what is the length of this distance here along the bottom of my triangle. Again, I'm producing a right angle triangle, and Pythagoras only works with right angle triangles. And so we know that the area of this box here plus the area of the box down below, these two add up, produce this big box at the top. So I'm going to take a box, and I'm going to create a box that fits in that spot there, and I'm going to ask the computer to calculate for me what's the area of that new box. And I can find that the area is going to be 19.1 subtract 5.25, because these two together have to add up to this piece. This subtract this will give me the area of this piece. So I'm going to get the area of 14.93, and if I happen to change the size of these things, you notice it all changes. Again, I can turn it around so it doesn't make any difference, but I am maintaining this right angle, and Pythagoras is talking about right angle triangles. So with a right angle triangle, the area of this box plus the area of this box produces the area of this box, and so I'm just going to show that, and that shows that there. So we've got area A over here on the left hand side, and I'll make that one color in green, and so the area is 5.46. The area in yellow, which we said we're going to take the blue area, subtract the green area, gives me the yellow area. The computer calculates that to be 14.93. If I add the green and the yellow, the 5 and the 14, I get 19.84, which is what the computer tells me the area of part C is. And just to show that it changes, if I change my numbers around, my green is now 10, my blue is now 39, so 39 subtract 10 gives me 28.65, and if I add 10 plus 28.65, I end up getting back to my 39.52. So I can solve for the missing blue piece or the missing yellow piece. And again, I originally wanted to find out what was the length across this line here, the top of my yellow box, and so I know my area is 15.6. For the whole square, 15.6 centimeters squared, I want to find the length of one side, so I take my square root, which tells me what's the length of the side, and I take the square root of that 15.6, and I get 3.95. So the distance from this blue dot to the purple dot is 3.95 centimeters. Now in this configuration, I'm looking to try to find what is the length between the red dot and the purple dot. So that's what I'm trying to find now. So I'm trying to find the green box here, so I can figure out what is going to be the length of this line right here. So I know that the little box that's going to be occurring there, so if I start and I make my box here, and I'll change its color to green, so that it matches the other diagram, we know that the green box and the yellow box has to equal the blue box. So if I take the area of the blue box and subtract the area of the yellow box, I can find the area of the green box. So I'm going to have the computer do that for me right now. And so there it is. The blue box has an area of 19.06 square centimeters. The area of the yellow box has an area of 14.5. So if I go blue, subtract yellow, I should find the area of my green. So the area of the blue, subtract the area of the yellow, gives me an area of 4.5. And if I change the size of my diagram, where do I have to go? There. I can see my numbers change. So 37 subtract 14 gives me 22. And 22 plus 14 gives me 36 and some change. So 37 is the same number. So it works no matter if I change my diagram. Now, I didn't want to find the area of the green. I wanted to find the length of this piece here. So the symbol that I need to use is my square root symbol. So I'm going to find the square root of this green box. And so I'm just going to have the computer do that. So I go up to the number, I ask it to calculate. I want to find the square root of this number here, and it calculates that for me. So this length here from L to R1, which is the line that I was looking for, has a length of 2.34. And 2.34 times 2.34 gives me 5.45 square centimeters. So my original question, what is the distance from L to R1? And now I know, 2.34 centimeters. So Pythagoras talks about finding the lengths of the pieces of my triangle, but really what he's talking about is the relationship of the area of the squares when I make a right angle triangle. And this is why the formula is what it is. So we could write the formula. It's known as the Pythagorean theorem, the Pythagorean formula, or Pythagoras' formula. The A plus B equals C, A being the area of the big square, B being the area of the A is the area of the green square, B is the area of the yellow square, and C being the area of the big blue square. However, most of the time that's not the way that you see it. Most of the time you'll see it this way. So little a is this length here, so of the green square. So little a squared gives me this big A area. So little a squared plus little b squared equals little c squared. And again, it doesn't matter if we change our diagram around, move it around from one side, if we change the size of it, if we go back and we talk about flipping my diagram around, if it spins, the formula still works as long as I have a right angle triangle and 3 squares. So there's a short demonstration of Pythagoras' theorem, and we can use it. There it is there, a squared plus b squared equals c squared. We can use it to find the areas of the squares. We can use it to find the lengths of the sides of my triangles, and we can see how it works and how all the pieces come together.